All right, so this is the fourth and final video for section 7.1, wherein we're calculating three different ways of getting confidence intervals for data that came from a normal distribution. This is the third way. So in this setup, we have two data sets. X sub i's come from a normal population with mean mu1 and variance sigma 1 squared, and y sub j's come from a normal population with mean mu2 and variance sigma 2 squared. By the way, pause, copy, play. Now, the xi data, I have n sub 1 data points, and for the y's, I have n sub 2 data points. And I don't know either sigma 1 nor sigma 2, all right? I'm looking for an approximate 1 minus alpha 100% confidence interval for the difference of the population means. And I've got this result here as the confidence interval, where S1 squared is the sample variance of x1 up to x sub n sub 1. So that'd be 1 over n sub 1 minus 1 times difference of means, data point minus sample mean squared added together. Okay, and S sub 2 is the sample variance of y sub 1 dot to dot y sub n2. Okay, and here's the issue part. Q is the 1 minus alpha over 2 quantile of the t distribution with script v degrees of freedom, where script v is all this monstrosity. So that's an S1 squared over N1 plus an S2 squared over N2 quantity squared, dividing by the sum of us S1 squared over N1 squared over N1 minus 1 with S2 squared over N2 quantity squared divided by N2 minus 1. So, you know, you just got to write that thing down. Am I going to expect you to have that memorized for the exam? No, this will be provided, or you can put it on a note card or something, right? All right, but still, we're looking at very much a similar format. Test statistic plus or minus quantile times some measure of deviation, all right? All right, let's do an example. All right, so pause, copy, play. So we could imagine this is back to the North Carolina baby birth weight data set. I've got 848 boys in my data set, and I've got their sample birth weight is 3,337 grams, and their sample deviation is 548 grams. I've got 739 girls with sample birth weight 3221 grams and sample deviation 551 grams. And I'm looking for an approximate 95% confidence interval for the difference of their population means, mu boys minus mu girls, okay? All right, so solution, using that formula from the last panel, I'm gonna calculate S1 squared over N1 plus S2 squared over N2. Crank that out and I get about 764.96. I did some rounding when I copied the answers down, but I didn't do rounding much in my calculator work. Okay, so let's calculate script V. That numerator this value got squared for the numerator. And then I have my 548 squared over 848 quantity squared over 1 less than 848. And my 551 squared over 739 squared divided by 1 less than 739. And that cranked out to give me 1553.15 degrees of freedom. Yes, degrees of freedom can have decimals, okay? I then handed this off to R to get my quantile. So Q is this is the command I typed, quantile for a t distribution. Since I'm after a 95% distribution, I want to know where the 97.5% mark in the distribution is. The negative of that will be the 2.5% mark. So 97.5 with that many degrees of freedom, and I got 1.961. Cool. All right, then there's my confidence interval approximation. Sample mean of boys minus sample mean of girls was -3. Q was the 1.961. And this square root, I took the square root of 764.96 and got 27.66, cranked it out, and I got to there. So my 95% confidence interval is basically negative 57 to positive 51 grams. Now, interpretation here, if my null height was that mu of the boys minus mu of the girls is 0, this confidence interval is saying, well, I guess we shouldn't reject that, because keep in mind, if I had 100 samples of data like this one with 848 boys and 739 girls, and if I did a confidence interval for each one, then 95% of the time, the mean would be in that confidence interval. And I'm looking like 0 being in this confidence interval. which would correspond to mu B minus mu G being 0. So this is not giving me convincing evidence that I should reject this null hypothesis. Okay. All right, one last quick panel. All right, very quick here. So pause, copy, play. So the last scenario is what happens if we have X sub I data, Y sub J data, but they're paired, like the diving data, the semifinal score had to stay with the final diving score. Okay, so what if we had paired data where I didn't know my sigmas and I wanted to get a confidence interval for their difference? Okay, well, so we're looking for a confidence interval for the mean of the X population minus the mean of the Y population, and we don't know our sigma 1 or sigma 2, okay? So what we're gonna do is what we did before, and if you remember, I took these two data sets, semi-final diving scores, final diving scores, and I just combined them into a single data set. So I'm gonna take my X sub I minus my Y sub I and define that to be a new data value, D sub I, difference, let's say, okay? Now I'm down to one data set. I still don't know my sigma, but now I can just do the T confidence interval as we work through in the second confidence interval discussion we did in section 7.2. That was where the data was normally distributed. A difference of normals is still normal, where I didn't know my variance or my standard deviation, okay? So, and that's basically what we did in chapter 6, I believe, or in an earlier chapter when I had paired data, I created a single data set out of it. Okay, so next section will be 7.2, and we'll talk about general confidence intervals.